Okay, section 3 of chapter 32 deals with Coulomb's law. Now, Coulomb's law relates the electrical force between charged particles to the size of the charges and the distance between the two charges. Remember, we've already discussed that like charges will have a repelling force. So two positive charges will repel, two negative charges will repel, and that opposite charges will attract. So a positive charge and a negative charge will attract each other. This equation is showing us how strongly they're going to repel or how strongly they're going to attract. So F stands for force. K is just a constant, so don't worry too much about K. Q1 is the charge of the first particle. Q2 is the charge of the second particle. So you can see that we are multiplying the sizes of those charges together. So that's up here where it says that the force is directly proportional to the product of the charges. So if the product of the charges is twice as big, the force between them will be twice as big. If the product of the charges is 4 times as big, the force between them will be 4 times as big. It is also inversely proportional to the square of the distance between them, and d is the distance. So we can see there that because it's on the bottom of the equation, it's going to be an inverse relationship. So that means that if the distance between the two charges, let's say, was 1 meter, and then we move the charges so that they are, or move one of them so that they are 2 meters apart, we have now doubled the distance. But as they get farther away, it's an inverse square relationship. So if they're going to, as the distance increases, the strength of the charge, the strength of the force decreases. But it doesn't decrease. It's not a simple relationship, it's a squared relationship. So if we double that distance, we have to square that, so it's actually going to be 1/4 of the force. We measure charge in a unit called coulombs, which is abbreviated with a capital C. 1 coulomb is equal to the charge of 6.24 times 10 to the 18th electrons. That's billions of electrons. It's a very large number. It just so happens that it is the number of electrons that would pass through a 100-watt light bulb in 1 second. So if you think of the old light bulbs that have the wire running through them, the incandescent light bulbs, 1 coulomb would be the amount of electrons that go through that wire in 1 second. So it's a lot of electrons going through there. And then just remember, we kind of touched on this in the last section, that most objects have an equal number of protons and electrons, an equal number of positives and negatives, which means that the repulsive forces and attractive forces are going to cancel out. So, for example, an electron is attracted to a charged particle 1 meter away with a certain amount of force. What will happen to the force's magnitude if the distance is doubled? And second, is the charged particle positive or negative? Well, we know that if we double that distance and make it 2 meters, because of the inverse square relationship, when we double the distance, we are going to cut the force in a fourth. So it'll be 1/4 the magnitude that it was before. Now, is that charged particle positive or is it negative? We said that it is an electron that is attracted, so this must be positive, because remember, opposites attract. This comes from one of your concept development sheets, so if you're having trouble, this should help you out. So this model here represents a hydrogen atom. 1, label the proton with a positive. 2, label the electron with a negative. So know that the protons are in the nucleus, and the nucleus is in the center, so we're going to put a positive there. A hydrogen atom often is just a proton in the nucleus. It doesn't even have a neutron. And the electron is this one outside that's orbiting, so we're going to mark that with the negative. Now, if this distance between these two, we know that they're attracting because they have opposite charges, but if that distance were to increase, so let's say that electron was way out here, because they're farther away, that is going to be a weaker attraction, a weaker force of attraction. If that distance were to decrease, if they were to get a lot closer, as the distance decreases, the force between them increases.